thank you, Ian, and thanks to all the organizers. It's a pleasure to come here. So thanks for inviting. And the title of the talk is a tribute to Chris Fuchs. He has a paper which is entitled Quantum Mechanics as Quantum Information and Just a Little More. So here I pretend to be more powerful than that. Surely Chris was very inspirational for the whole research program. And the thing starts with this work that I did in collaboration with Mauro D'Ariano and Giulio Chiribella, where we had first of all, a framework of operational theories, and then a set of axioms that pin down in this framework in this scenario of possible theories exactly the formalism of quantum mechanics. And this approach is a view on quantum theory as a information theory in the first place. So everything which is about quantum systems is actually every feature of quantum system is thought of in the first place as a feature of information carriers rather than elementary particles of nature or constituents of matter. So the thing is that with this reconstruction of the language of quantum mechanics, we don't have any mechanical concept in it. And the idea would be, one thing that one can do is to take classical physics and then quantize the classical concept, which is a typical approach to quantum theories. It's quantization of some classical field theory, for example. However, what we would like to do with this approach is to push the informational approach further and see if we can, with further axioms and further assumptions about what is a physical law in this picture and what are the features that characterize it, to reconstruct also the mechanical concepts like space-time in the first place. And so this is what the workshop is about: reconstruction of the geometry and mechanics in it. And the bottom line of my seminar would be to show that if we can reconstruct in some sense geometry in this framework, the idea is that geometry is not an object by itself, but it's just a way of phrasing physical laws which are more primitive. So first you have physical laws, dynamics, and then geometry just appears as a very reasonable way to represent the dynamics. So let's see how you can start thinking about physical laws in this scenario where you have information theory in the first place. And the first thing that I would like to recall is this quote from Laplace, which is the picture of the classical universe, which I think still informs a lot of our understanding of the way in which we interpret the fundamental physical laws. So everyone is okay probably when he studies quantum mechanics, introductory quantum mechanics, but then you start studying relativistic quantum mechanics, and then I think somehow you come back to some more realist interpretation of quantum theory. In field theory, the measurement problem disappears at all. You're not taught about measurements in quantum field theory. That there's a problem with local measurements in quantum field theory, indeed, if you want to make a consistent theory of it. So the picture of Laplace is that of a big clockwork. The universe is a big clockwork where everything is determined by the state of matter at one given time. So as Laplace says, if you have an intellect which is powerful enough and knows everything about the universe at a given time, then for him, the universe in the far past, in the far future, becomes just the same thing. It's completely computable from the information about one time in the universe. And of course, this word view is disrupted by the advent of quantum mechanics, which is probabilistic in itself. You have some problems with the incompatibility of different quantities that you can measure on a system. But I would like to save something in this worldview of Laplace, which is a very modern idea of this intellect, which is basically a computer, we would say in modern language. So let's say that the physical laws are such that it can be thought of as an algorithm that you can provide to a computer to predict everything which is predictable in the end of the day, which is maybe not exactly all the things that Laplace has in mind, so every position of every single particle in the universe at every time. But what we can say about the universe can be computed by a computer. This is the idea behind the seminar. And this is instantiated in this idea of the suggestion of Feynman. This is a famous paper because 1982. This is the paper where Feynman introduces the notion of a quantum computer. It's not the only one. Also, David Deutsch did it. But the interesting thing about Feynman is that he was playing this kind of fundamental game. Feynman didn't like to talk about foundations, but in this paper he does somehow. And he wonders what would physics look like if we had a computer that perfectly simulates physics. And he claims that it has to be a computer with finite elements. So if you want to describe a finite portion of the universe, you don't need infinitely many elements, which means that, as like Feynman says, that if this is to be true, then the physical laws that how we know them today are to be corrected, somehow have to be changed. So the idea of Feynman was to describe systems, evolving physical systems, as basically cellular automata. So now the first part of the talk will be dedicated to the introduction of cellular automata in a quantum scenario. And then I will use them to show how to approach the idea of reconstruction of mechanical laws from an information theory. So a cellular automaton was introduced, the concept of a cellular automaton was introduced by von Neumann in the 50s. And of course, in von Neumann's purpose was the idea of axiomatizing a concept like a self-reproducing machine, self-reproducing entity. But for this purpose, he introduced what we would call today a cellular automaton, which is, you can think of it as an array of bits, for example, which might be one-dimensional or two-dimensional or in any geometry. Every cell contains a bit, and then you have a law that calculates a function of a little neighborhood of a cell, and with this function evaluates the value of the bit at the next generation, at the next step. So this is the simple evolution. The idea is you have a simple local rule which is the same everywhere and generates the dynamics of the system. And despite the rules are simple, cellular automata can exhibit complex behaviors in the large scale, which is interesting because that's exactly what we would expect from physical law, something which works simply on a small scale, but gives rise to the complex behaviors of physical systems that we know in everyday life. And for example, you have the game of life, which is one of the most famous cellular automata that already has these features. It's computationally complete, so it's equivalent to a Turing machine in the first place. And if you program initial states on a game of life, you can have very different behaviors, like this pattern is static, so it will stay like that forever. This one oscillates, it starts changing pattern, but at a certain point it becomes periodic, whereas this one is a glider, it keeps moving forever in the same direction. So very simple rules, very various, very complex and various behaviors. So what can we say about cellular automata in the quantum world? How can we formalize this thing if the cells are qubits or quantum systems in general? So the idea is that one, first consider a finite grid. So with periodic boundary conditions, maybe, in order to not to break the translation invariance of the thing, but it's a finite system. So every cell is associated with a Hilbert space, or better, with an algebra of operators on the Hilbert space. Then you have a huge tensor product, and then the cellular automaton would be, in the first place, a unitary operator. Okay. A unitary operator on the grid, on this big tensor product Hilbert space, which has to abide by some requirements. The first one is locality. So if you take operators in a given cell, like the red cell, and you do the evolution for one step, what you get is an operator which is localized on a small portion of the thing, which is the neighborhood, which is the one that I highlighted in blue here. And then this allows us to define the neighborhood of a cell, and already gives a pre-geometry to this thing, because immediately you realize that you have light cones, the analog of light cones on this structure, because information can propagate at a finite speed at each step. So every cell has its future cone and past cone of causal influence. And this is the main reason why cellular automata are very inspirational to try and find an evolution of information that can be put in analogy with some physical evolution, physical laws. So the first thing to do is to define this thing in an infinite scenario where you have, of course, one cell, which is a Hilbert space like before, or an algebra like before. But now what you want to define is the infinite tensor product of things. So you have to go through some steps. It's standard in the theory of sister algebras, but I will show you the construction. I think it's interesting for those of you who don't know it. It's the idea of quasi-local algebra. So the first thing that you do is to identify again every cell of the grid with a quantum system. So Hilbert space or algebra, better algebra of operators acting on that Hilbert space. And then you think of a larger region that contains the original cell. And then you realize that this algebra of operators of that region there can be imagined as a subalgebra of the algebra of operators on the big region. So you take this larger tensor product, you consider the cells in the orange region, and you think of the operators in the red cell as operators actually acting in the larger region, but just by extending with tensor product on the cell which are not interested about the red one. So this algebra is somehow a subalgebra of the larger algebra of the region, and the embedding function is this one. You can embed the algebra of the cell x0 into the algebra of the region R, but just tensoring with identity. And then you can do this with larger and larger regions. Yes, yes. An Ising model will fit this framework for sure. Then this is for operators on the Hilbert space. So in the case of the Ising model, the classical Ising model, of course, is not the quantum, but you can take the quantum Ising model, and then you have spins in every cell, and that's it. But then this is just for the operator algebra. Then you have to define the dynamics of these things, and this can change. So you can move from the Ising model to the Hubbard or something else. So now you have all the finite regions on your lattice, and then you have these chains of regions that are contained into each other, and you define the embedding functions always in the same way. You take operators on a region, let's say the orange one, you want to embed them in the yellow one, then what you do is to extend a tensor product with identity. So the nice thing about this is that if you have two distant regions or overlapping regions, you can always embed both of them in the union of the two regions. So even though you have operators which appear not to be comparable in the beginning, you can always embed them in the same region. And then the consistency of this construction is given by the embedding functions. So the embedding functions must abide by this condition. So if you embed an operator in the same cell where you define it in the first place, then it's the identity mapping. And if you apply two embeddings in a sequence, so first you take a region J, you embed it in I, first I in J and then J in K, it's like embedding directly, immediately I in K. So you start from the red one, put it first in the orange one, and then in a second step in the yellow one. This would be the same as starting from the red one and embedding it directly in the yellow region. This is the kinematic part, so it would be the same. So in lattice QFT, you start with a lattice and define algebras operators on the nodes of the lattice. But then the difference will come later, because here you impose unitarity and time is discrete in the first place, whereas in a lattice gauge theory, lattice field theory, you would define an action, which is a function, and then you use the action to try and define a dynamics, but you're not granted to have a unitary one. So the problem would be to enforce unitarity in that situation. Whereas here, we have unitarity as a postulate, as we will see. No. Yes, I couldn't draw a 3D one, but that's the only reason. So it might not even be z to power d. It might be a different kind of graph with a different geometry. So, okay, and then you define the algebra of operators on the big thing as this collection of local operators in each conceivable finite region of this thing. And then you have to just quotient by an equivalence relation that tells you, okay, these operators are the same, just imagine into different regions. So if you try to think of this means that suppose you have two operators bj and bi on two different regions, and then in the first place, you define a third region K that contains both of them and embed BI and BJ in this larger region K. So if you end up with the same operator, this means that you were describing the same operators into different regions in the first place, so this must be equivalent. And this is the equivalence relation by which we quotient the union of this large set of local operators, and this is the inductive limit algebra. This algebra represents all the local operators on your lattice. And then you have to complete this one because you can have a norm on this algebra, which is the operator norm. And you would like to give an interpretation to this operational norm, which is actually interesting because it's related to the possibility of distinguishing the action of two operators. So physically, if two operators are different, you have physically a procedure to distinguish them, and you have a success probability that is proportional to the norm distance of these two operators. So you can define Cauchy sequences according to this operator norm, and equivalence classes for Cauchy sequences, and then you construct the topological limit exactly as you do when you construct the reals from the rationals. So you define a real as an equivalence class of Cauchy sequences of rationals. And there you get also operators which are not local, but they are elements of the so-called quasi-local algebra, which means these operators can be approximated arbitrarily well by local operators. So this algebra contains all the operations that maybe are not local, but only those ones that can be approximated with arbitrary accuracy using local operations. And this is the algebra that will be the universe for our cellular automata. So now, what is a quantum cellular automaton? It's an isomorphism of this, an automorphism of this quasi-local algebra. So you can think of operators located in one cell, apply the automorphism, and then you impose in the first place locality. This is the first requirement. So if you take operators in a cell, you end up with operators in a finite neighborhood, in a finite region. And the second requirement that was introduced in the definition of cellular automata can be removed in some situations if it's convenient, but typically we will consider translation invariant cellular automata is exactly translation invariance. So translation means that you have this homomorphism that takes the algebra of one given cell and displaces it by some amount, z. And the action of the homomorphism must commute with this translation homomorphism. So if you have a cellular automaton, quantum cellular automaton, you have the notion of a local rule. So you can restrict the action of the cellular automaton to a given cell, let's say cell X, and then the homomorphism from the algebra of the cell X to the algebra of the neighborhood is the local rule of the cellular automaton. And the interesting thing is that due to locality and translation invariant, you can summarize that all you need to know about the cellular automaton in this simple local rule. So in the first place, translation invariance allows you to define the action on an operator located, let's say, in a cell X like that one, by first translating the operator in the cell node, the origin of your lattice, then applying the local rule in the origin, and then translate back the image to the final place you want to see it. So the local rule is everything you need to know to characterize a cellular automaton, of course, along with the structure of the lattice. And there's a theorem that grants you that every local rule, every homomorphism of a full matrix algebra is of this form. You can tensorize with identity, and then just the freedom you have is just a unitary isomorphism. So which means that local rules can be imagined in this way. So you see that. No, if it's not a full matrix algebra, then this theorem doesn't hold. So it will be more complex in that case. So it really has to be a full algebra. So which means that if you want to know the image of operators in a finite region, then you can think of these operators as sums of tensor products of operators, and then you can calculate the image of this big thing just by taking the sum of the products of these images. And you can do this because if you start with operators in different cells, they commute, and then since the quantum cellular automaton is an automorphism of the algebra, also the images will commute, and then this product will be well defined independently of the order in which you perform the product. This is an important thing, and since this is an isometry, then the local rule allows you also to calculate the image of the limits, because you can take the limit of the images of the elements of the sequence that define your element of the quasi-local algebra. So the important thing then you realize is to characterize the local rule. If the local rule is in correspondence with the cellular automaton, and if you understand it, you've characterized it, then you're done. One thing that we know is a necessary condition. That is, if you take the image of two operators located in different cells, they must commute, even though of course, the neighborhoods might overlap, like in this case. But then, anyway, the images must commute. Interestingly, this is a necessary and sufficient condition. So this characterizes the local rule of cellular automata. So if you can find the local rule that abides by this condition, then you can define the cellular automaton, because you can define in the first place the action on local operators, on tensor products. The action on tensor products of local operators is like that. You define the cellular automaton on these tensor products as the product of the images. And this is well defined because they commute. Now it's your hypothesis. They commute, then you can define this thing. And then local operators are linear combinations of tensor products. Then you just take the sum of the images and you have the image. And since all these local rules are of the form that I showed you before, conjugation by a unitary of identity tensor operator is isometric, and then this allows you to evaluate the action of the cellular automaton also on the limits of Cauchy sequences. So the condition, the important point is that this condition becomes a necessary and sufficient condition to characterize the local rules of a cellular automaton. And interestingly, these conditions are not sensitive to the boundary conditions on your grid, which means that you can, for example, start from an infinite grid like that one, build a torus, and you see that the condition would be dependent only on the local structure of the cell, which is let's say, the simplification of what I call the wrapping lemma, what is called in the literature actually the wrapping lemma. And the thing is that you can characterize cellular automata on this structure, find the local rules, and then you know that these are exactly all the local rules you can have also on the infinite lattice. Okay. So this simplifies by far the characterization of cellular automata on a given structure. Okay, so now this is the theory. This is the kind of objects and tools we work with. I will try to convince you that it's possible to find the emergence of physical laws using cellular automata. And this connects to some ideas that already unsuspectable scientists had about the structure of the macroscopic structure of space-time, of geometry. One is Riemann himself, that considers the idea that the geometry might be actually on its microscopic scale can have a discrete nature. So in this paper, he discusses the possibilities, the two different possibilities. So geometry emerges from a discrete framework, or geometry is continuum in its bone. And he has no opinion on this. And another, even more unsuspectable, is Einstein, which actually says, there's a drawback with the continuum, and he thinks that the miscarriage of general relativity with quantum theory might be in the fact that we use a continuum to describe the motion of finitely many elements. Let's say finite number of moving points in Einstein's words. So he would like to have a discrete background, but he didn't do that just because he said we lack the mathematical structure by that time. But he tried to do that. He struggled, actually. So the proposal is this one, comes from, but I will discuss this later. The mathematics now is there. It was, oh, thank you. It was introduced by Gromov, which Mikhail Gromov initiated the discipline of geometric group theory, which is a discipline where you describe discrete groups through graphs, and we will come to that a bit later. And the geometric properties of these lattices connect with the algebraic properties of the groups that are represented by the graphs. And these are the kind of connections between algebraic properties and geometric properties that are sought in geometric group theory. But this turns out to be one conceivable mathematics that allow you to do what Einstein was looking for. So try to have a discrete underpinning of a continuum picture of the physical laws. So let's try to play this game now. Suppose that you have the numerable set of systems. Now I consider fermionic systems for reasons that I don't have time to argue here, but we can discuss them maybe later if you're interested in it. So this is unstructured. So it's just enumerable. You can put labels on them just to distinguish them. But by the time now, by this time, these labels have no physical meaning, have no spatial meaning. They're not geometric in the first place. So now, the only thing you have are the anti-commutation relations that define the fermionic fields. And now you introduce your cellular automaton in the usual way, but you don't have a geometric picture. So the only thing you ask is that the image of operators of a given cell are contained in a finite number of cells, which is you will define later as the neighborhood. So for example, if cell 6 is in the neighborhood of cell 2, then you draw an arrow from 2 to 6. And then in this way, you immediately realize that you can construct a graph. Okay, the graph of causal connections, just because the evolution is local. So locality tells you that the neighborhood, for example, of cell 5 is given by cell 4 and cell 1, because these are the only two ones connected by arrows to that one. Then you require reversibility. And the requirement of locality is that the size of the neighborhood is bounded. Okay. So you cannot have system interacting with arbitrarily many other systems. So once you have this, you can, for simplicity, take the linear case. We'll start thinking about the linear case because everything is simple. But as I showed you before, you can do exactly all this part of the geometric construction of the graph on a general case. In the linear case, the evolution of field operators is just a linear combination of field operators in the neighboring cells. So the neighborhood is characterized by these transition matrices. These are the couplings between the array of field operators in one cell with the array of field operators in another cell. Cell J, cell I. So if the transition matrix is different from 0, then set J is in the neighborhood of set I. Cell J is in the neighborhood of cell I. And so in the linear case, the neighborhood is characterized by these transition matrices. And then you impose, so now you have this evolution, and the only thing you require by now is reversibility. And then the second thing is that you impose is homogeneity. You can phrase this very abstractly, information theoretically only. And the requirement is basically that you can distinguish the role of two different systems, looking at the way in which they evolve. But you can distinguish them, but only if you choose a third reference system. So if I'm here, then I can distinguish, for example, this point and that point in space. But absolutely, if I look from outside the universe, then the physics of these 2 points is indistinguishable. They don't have any special label in it. The symmetry is just broken by the initial conditions of the system, so the state, but not the dynamics. So this requirement of homogeneity allows you to show that actually the graph that you construct with your evolution, the one of causal influences, the neighborhoods of your cells, is a very ordered one. It's a Cayley graph of a group. The Cayley graph of a group is a way of presenting the group. So the group is like that. Every node of the graph is an element of the group. You can choose one element. They're all equivalent, but you choose one as the null element, the neutral element of your group. And then the construction of the graph works in this way. You have a set of generators, which are the colors of the arrow here. So, for example, in this group, you have 2 generators, the blue one and the red one. And then an element of the group is given by the path that connects the origin with the neutral element to that element, to that node of the graph. So, for example, let's say red, blue, red to the -1. This sequence of elements of the group is an element of the group, will be identified with that point. So this is a graphical way of representing the algebra of a group, of a discrete group. And then the evolution by construction in this way is translation invariant on this group. So if you think of translations in this group, the evolution from which you built the graph itself is translation invariant with translation on the graph. So here comes the role of geometric group theory, because one of the key elements in this discipline is the notion of quasi-isometry, which is this relation between metric spaces. So you can have 2 metric spaces. Of course, a graph is a metric space because you can define a distance on the graph. For example, the distance between this point and that point will be 2 because this is the shortest path that connects the first point to the second point. So the graph is a metric space. Is one special instance of kind of spaces that are interested by the notion of quasi-isometry. And then if 2 metric spaces are quasi-isometric, if there's a mapping between the 2, the mapping that I call E here, such that the distance between 2 points in the original metric space is similar to the distance of their images in the image space, up to multiplicative constants and additive constants. Okay. So this is quasi-isometry, it's almost isometry. And the other requirement is that if you take any point in the group G, then there is an element of the first group whose image falls in a small sphere of a given radius within point Z. So the image of the first metric space almost fills the second space. A and B are fixed. Yeah, that's the yes. There's a quasi-isometry if there exists B and A such that these inequalities hold. So this is an equivalence relation between metric spaces, and then you can collect metric spaces in equivalence classes according to this relation. And the interesting thing is that if you take a Cayley graphs of group, you can always find a smooth manifold in its equivalence class, which means that there's a natural way of imagining this thing embedded into something which is more similar to the space-time we are used to think of. Okay. But the interesting thing is that this structure comes from the evolution of system in itself, the algorithm that updates the content of the arrays, the memory arrays of the cells of your cellular automaton. So you start from this evolution rule, you construct this graph, and then you identify essentially a geometry in which you can represent it somehow. Yeah, up to quasi-isometry, of course. Yes, at this stage, the lattice is fixed. This is I will try to argue that this is one naive way of thinking of the reconstruction of geometry. There are other ways we're trying to seek, but this is a very effective one. It already shows you that it's conceivable to have this discrete algorithm picture of physics, think of physical laws as algorithms, and then reconstruct also the geometry and the mechanical part of the theory. The dimension. It depends on the dimension of this lattice. Well, if you think of a billion groups, then you can embed them in a Euclidean space, and the dimension would be the same. Okay. So if you have z to power d, then you embed it in r to power d. If you have different groups, you can have hyperbolic geometries or other kinds of geometries. So now, you can expand the solution on plane waves, and transaction invariance will grant you that this walk operator will be diagonal on this basis. So all you have to characterize is this walk operator at a given wavelength. And the wavelengths constitute a pre-UN zone, which is a pre-UN cell of a graph. So if we did this on z to power 3, the group z to power 3, and not all the Cayley graphs of this group allow for a unitary evolution if you have a spanner with two components at each lattice side. In particular, for example, you can consider the simple cubic case of what each node has exactly 6 neighbors, so 2 in each coordinate direction. Or, for example, the body-centered cubic lattice. And it turns out, for example, that you cannot solve the unitarity equations on this structure, but only on that one. So this is the only lattice that allows for such an evolution if you want spanners with 2 components at each cell. And the evolution actually, if you solve the unitarity the solve equations for the unitarity conditions, you find a very restricted number of cellular automata, whose dynamics can be approximated, actually interpolated in a continuum. If you embed z to power 3 into r to power 3, and you expand the evolution, so these unitary operators are exponentials of separate operators, you can write down the corresponding differential equations, and you find Wiles equations. So essentially, you can reconstruct Wiles equations for just this requirement of unitarity and homogeneity and sort of isotropy in this purely informational scenario. And notice that we recover Lorentz invariant equations, Lorentz covariant equations, even though we didn't mention relativity at any point here. So somehow the geometry of a Minkowski spacetime emerges from the evolution that we imposed at the beginning. And combining the Weyl automata, you can also reconstruct Dirac's equation, so you can have a mass. And you can also reconstruct Maxwell's equations, taking bilinear functions of your field operator. So if you take 2 walks and you take the tensor product, then you will see that some excitations, some entangled excitations of this cellular automaton will evolve like photons in the vacuum. And this theory, by the way, is a kind of neutrino theory of light. So that theory where bosons are considered as composite particles, and in particular in this case, photons will be pairs of fermions. And you can also match the bosonic statistics in an approximate way if you construct the function in a suitable way. So now comes the problem of reconstructing geometry in a serious way, which is, for example, to pin down the problem, we can go back to this paper of Schild, 1947, in which he tried to construct actually a lattice, a discrete lattice, which is invariant under the Lorentz group, and try and see if the discrete is compatible anyway with relativistic covariance, which seems to be the case from our equations. But you have to interpret our the fact that the equations that we recover are Lorentz invariant, because, for example, Schild tried to find lattices that are invariant under the Lorentz group, some subgroup of the Lorentz group, and he found some, But unfortunately, the subgroup is such that the smallest velocity, which is non-zero, allowed is 0.866 the speed of light, which is, of course, was too much for our case. So we have a proposal to get around this problem, which is to turn the relativity principle on its head. So define changes of inertial frame in this scenario where you don't have geometry on the fundamental level, in terms of the symmetries of the physical laws, our cellular automaton. So we have a mathematical description of the cellular automaton in terms of constants of motions. For example, the wave vector and the eigenvalues of the unitary evolution operator. And we want to have a mapping of these parameters such that the cellular automaton, the description of the cellular automaton remains the same. Basically, the eigenvalue equation for the unitary evolution remains the same. And if you pin down those symmetries, then you find that it's a realization, actually, not a representation, but a realization of the Poincaré group, semi-direct product with some scaling group, in terms of diffeomorphism of the Brillouin cell. So, for example, if you take the orbit of a wave vector under rotations around an axis, it will be a circle if the modulus of your wave vector is very small, and then you will start seeing deformations if you take very large wave vectors. These are the orbits of boosts, which look like boosts in this area, but then become very distorted if the boost is by a very large speed. And this is the orbit under the full rotation group of a wave vector in the high K regime. So you see it's not a sphere, it becomes this kind of bell pepper. So it's possible to do that. You can reconstruct the space-time with changes of inertial frame, and the representation of the change of inertial frame is still the Poincaré group, basically. The problem is how to interpret these deformations that you see here or there.
So can you explain again what is this procedure of picking an inertial frame and then changing to another one?
Okay, you define the change of inertial frame as a function on the wave vector and the eigenvalue of the evolution operator, such that if you apply this function, you get other solutions of the eigenvalue equation for the evolution. So this means that your change is just a change of representation of the same evolution.
Right, but so this function has to be invertible or something?
It turns out to be invertible. It has to be invertible because you want the dynamics to be exactly the same. So for each solution in one reference frame, you needed to have a solution in the other one.
Right.
So this is one of the requirements.
And then you study the structure of all these transformations, and it turns out to be the Poincaré group.
Exactly.
Okay. Nice.
Then you also have a semi-direct product of the Poincaré group with another group, which is, so the idea is taking a Brillouin zone for the BCC lattice, which is a polytope, and you want to embed it into the full space. So you have a function which becomes divergence close to the border of the Brillouin cell, but this function is arbitrary. And so the choice of this function is the group with which you do the semi-direct product. You have a choice of this scaling function, but any choice you do ends up in giving you the Poincaré group for the transformation of the wave vector. So it's a bit complicated, but we can discuss this later if you're interested. Like I said, the problem is now to interpret these deformations, because one point here that I would like to stress in the last part of the seminar is that, okay, here we reconstructed, for example, the evolution of free fields, relativistic free fields, but you don't see this evolution with your eye, of course. So this is not enough to reconstruct the physics of the system, because when you do measurements on a system to see what happens, you need to reconstruct the statistics of those measurements. You need a measurement theory, and this is what is physical about the theory: the predictions of outcomes of local measurements, and not just a mathematical picture of the dynamics. And so the problem would be to have a measurement theory, which is the very last chapter of the seminar, and also a way of an alternate way of reconstructing the dynamics at a large scale, because the construction that I showed you with this reconstruction of the dynamics in terms of differential equation and then the interpretation of the symmetries in terms of changes of reference frame is very much related to the fact that we use linear cellular automata, and they have a simplified picture. We can do this easily. But if you don't have this, we would like to define the continuum limit in a more rigorous way. And that's why we started studying renormalization of these things, cellular automata. Renormalization would be a technique. The Kadanoff, actually, the Kadanoff approach would be just a technique to relate the large-scale behavior of your systems when you know all the microscopic details of the theory. A lot of those details are not relevant for the large-scale physics, but for example, if you set the lattice step to the Planck length, then you want to reconstruct maybe the physics of high energy that you see at the LHC. You have a large number of orders of magnitude of difference there. So actually what you want to describe is a picture on a large scale, but you have a very fine-tuned grid, and you want to wash away the irrelevant degrees of freedom on this picture. So what you do is to group the cells in larger cells and see if the dynamics is such that you can describe this large-scale dynamics with another cellular automaton. Actually, what you would like to do in the end of the day would be to have a field theory here, not another cellular automaton, but we started with this question: how to renormalize the cellular automaton to another cellular automaton. So the idea is the following. So it's an instantiation of this study on classical cellular automata that was initiated by Israeli and Gondelfeld. We adapted the approach to quantum cellular automata. So you take a cellular automaton, you apply it for a given number of steps, let's say n steps, and then you wash away degrees of freedom by co-isometries. So you take the full space and you project it in a smaller space. So this space will be isomorphic to the one of a single cell of the original automaton. And what you would like to have these dynamics to be exactly the same as that you would get if you washed away the degrees of freedom in the first place and you just took one step of the new renormalized cellular automaton. Okay, so this is the equation for satisfying the renormalizability condition. So T is renormalizable to S if there's a co-isometry that does this work. So we studied the simple case of qubit cellular automata in one dimension because they are fully characterized. They all have this structure, which is, you see, is a brickwork of finite gates. These are control phases followed by local unitaries. So this is the most general transition invariant qubit cellular automaton in on a one-dimensional structure. And we characterize the full renormalization flow in this case. So the only renormalizable cellular automata are actually the trivial ones, so without interaction between neighbors, local unitaries. This is, of course, trivially renormalizable. Then you have those ones where the unitary is actually a rotation around the z-axis, which is the same one where you define the control phase. So everything is, every gate here commutes. Then in this case, you can have a flow, a non-trivial flow. And finally, the case where you have sigma y here. So exactly a rotation in along a direction which is orthogonal to the z-axis, the one in which you define the control phase. So this is a case where you can work out the renormalization flow completely. You can also find non-trivial fixed points of the renormalization flow thanks to these possibilities. So, of course, this is just the beginning of that study, and we would like to push it a bit further to encompass also different geometries, because the one-dimensional chain is very easy, but also larger cells, larger local cells, and fermionic systems. So the first thing that we are doing is to, actually we are doing it right now, is to do the same thing with fermionic cellular automata in one dimension. And finally, the last part of the seminar will be dedicated to the theory of local measurements on this structure, which is inspired by these works. The first one was by Sorkin, in 1993, he realized that if you take a field theory and then you do local measurements like those ones on a finite region that intersects with two disjoint light cones, and you wash away the outcome of this measurement, just don't even read it, but just because you did the measurement, you can have signaling from this light cone to that light cone. And he calls those impossible measurements. So there are local measurements that are in conflict with the structure, the Minkowski structure of quantum field theory. And this was studied more in detail by Aronov and co-workers and Gisèle Del Santo very recently. So what is the workaround we are proposing? So our structure very naturally allows for a picture of local measurement which is not in conflict with the causal structure of the stellar automaton. So take this 1 plus 1 dimensional space-time, and suppose that the measurements you're allowed to do are just local measurements at given cells at given times. And then if you want to make actually a non-local measurement, what you can do is that let those local measurements interact through steps of the evolution. So all the non-locality that is there is the one that is introduced by the natural dynamics of the system. So of course, if these are the local measurements that you allow for, naturally you don't have this problem of signaling outside the light cones, because the effects of a local operations here only occur within the yellow light cone, and the effects of the red cell here cannot detect the action of those ones. So the question is, okay, you do local instruments at each point, local quantum instrument at each point, and then you would like to recover anyway, for example, Bell POVMs, entangled POVMs. Is it possible to do that? This is a question which is not easily answered, but for example, if you take a geometry like that one, and you use this whole space-time region to do your local measurements, for example, what we would like to recover is any conceivable POVM at this time on this region. This is the question. Is it possible to do that? Is it possible? Maybe you need to enlarge this region enough, but you would like to be able to approximate any POVM on that region. This is one order of questions about local measurement. And the other one is to reconstruct quantum instruments. So now you also want to see the dynamics of the quantum measurements. Is it possible to have geometries like these ones? The yellow instruments are used as initialization boxes. So these are just initialization, destroy and prepare a fixed state here. These are discard measurements, so that what is actually important in this scheme is just what happens in this bulk, which should simulate a quantum instrument like that one. So can you recover all the instruments if you allow, for example, for a suitably large time? So this is an open question, a difficult one, and we started to analyze this one. And again, we started with a simple case because these stellar automata are basically a few of the ones that are fully characterized, and studied schemes like those ones. So here, of course, you have only local measurements. Local instruments end up in local POVMs. But if you allow also for this layer of instruments, then what you get at this time with this pyramid of processes is LOCC POVMs. So non-local, but trivially non-local. Non-local, but with local operations and classical communication. But if you allow an extra layer, already at this stage, this pyramid of processes gives you POVMs which exhibit entanglement and magicness. This is a study of the entanglement entropy of the projectors of the POVM that you achieve with a given protocol. And you see, these depend on the phase of the control phase. Of course, if you put the phase to 0, then this decouples completely, and of course you cannot have any conceivable measurement because you remain with only local measurements. But as long as you activate a little phase, then entanglement entropy increases. And the protocol is not even optimized, and it's just a few steps. If you let this architecture to enlarge, then it's possible that this graph becomes steeper here up to some point where you actually end up with filling this space. That's the wish. This is a study of magicness instead. So I don't know how many of you have heard about non-stabilizer quantum mechanics or non-stabilizerness. So for example, a Bell state. Okay, if you just have a Bell state and you do stabilizer measurements, which means measurements that are spanned by operators that stabilize the Pauli group, then these processes can be simulated easily with a classical computer. So what you need on top of entanglement is also the fact that you can do operations that are not simulated by stabilizer operations, and which is the thing that you need, for example, to violate Bell inequalities. And this resource is called in quantum information theory quantum magicness. And you see maximal entanglement coincides with minimal magicness. So the most magical